Friends, welcome to the discussions on the finite element methods. In the previous video, we have discussed in part 1 about the one-dimensional two-node elements, where we have seen the fundamentals, derivation of the shape functions, and followed by the stress-strain relationship matrix. In the second part, we have seen the potential energy approach. We have seen the derivations of the element stiffness matrix, element body force vector, element traction force vector, followed by the assembly of global stiffness matrix and global load vector, and also the properties of the element stiffness matrix. In today's discussions, we shall see the treatment of boundary conditions in this third video. Right? This is how the students now the boundaries they need to be taken care in the equilibrium. Therefore, there is what called treatment of boundary conditions. Now, the boundary conditions may be of specified nature, means a few boundary conditions do have a specified displacements. They are what called specified boundary conditions, right? Such as like this, right? Are the boundaries or supports maybe of multi-constraint boundary conditions. Second type, right? Now let us see the very first type, the specified boundary conditions. Whereas specified boundary conditions may be solved either using elimination approach, or they may also be used using multi-constraint approach. Multi-constraint approach also. Now we'll see first um, specified boundary conditions using elimination approach. Right? Here, specified boundary condition means at the boundary, the displacements are specified. Students, the displacements are specified. Right? That is how the displacement value may be specified as 0, or the displacement value U6 may be specified as a particular displacement, maybe some 0.6 mm or 1 inch or 1 foot as appropriate. Right? Like this is how the values are specified. Generally, these are applicable for sinking of supports, right? Where in the sinking of supports, what we'll say that support is sinking by an amount of this delta, right? That is how the values may be specified, right? Now that is how we'll say the these boundaries are now specified as QP1, means degree of freedom along the first boundary P1 is equal to specified as A1. Here in this A1, in the if I compare with the above equation, that A1 is equal to 0 here, right? Or like that QP2 is equal to A2, or dash 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 up to QPR is equal to AR, where R is the independent, R independent is constants, AR is the number of independent constants, R is the independent number of constants, AR, right? That is how A1 to AR may be 0, maybe negative, or maybe positive, keeping in view the effect of the elements, right? Maybe they may be positive also, right? And that all depends upon for sinking of supports or temperature loads, etc., right? Then once these specified boundary conditions are solved by generally the elimination approach using minimum potential energy concept method, then how to get those solutions using this elimination approach. Solution means how to get the displacement, using elimination approach. That now we'll see for the specified boundary conditions, right? Then uh, here the minimum potential energy approach will be used in elimination approach, right? Now let us say the degrees of freedom vector is n by 1 vector, capital Q is n by 1 vector, which is q1 q2 dash dash qn n by 1 vector, which is transpose. Similarly, the global load vector f is n by 1 vector, which is f1 f2 dash dash, right, up to fn transpose, right? Similarly, the global stiffness matrix K is n by n matrix, which is given by K11, K12 dash dash up to K1n first row, like that. Last row is Kn1, Kn2 dash dash up to Knn student, right? Where the any general coefficient of this stiffness matrix is referred by Kij. Fine. Then once I have these, then I'll formulate the total potential energy, which is a product of Q transpose KQ, Q transpose KQ, right? That is how half. Now expanding that, now I have the terms like this: half Q transpose K11 Q1 Q1 K12 means this one operated upon Q2, right? So on and so forth. K1n operated upon Qn, right? Q1 K1n operated upon Qn. That is how the first row operated upon the this column vector matrix of the Q. Similarly, K Q2 multiplied by K11 multiplied by Q1 Q21. That is how the second row operated upon this vector dash dash up to last row, right? Qn, Kn1, Q1, Qn, Kn2, Q2 plus dash dash up to Qn, Knn, Qn. That is how the total potential energy of the system, one-dimensional continuum system, right? That of this continuum system, entire continuum system. Fine. Then that plus work potential, the work done by the different forces, right? Body forces, attraction forces, and concentrated loads, if any, right? Minus Q1 F1 plus Q2 F2 dash 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 up to Qn Fn. And there is the total potential energy. However, if the body were to be in equilibrium, then we know the law of minimum potential energy approach. That it's a differential with the R independent degrees of freedoms should be equated to 0, should be minimum, right? Then we'll say that dou pi by dou A1 is equal to 0, similarly dou pi by dou A2 is equal to 0, dash dash up to dou pi by dou AR is equal to 0, because AR is the independent constants, independent constant. Later onward, R plus 1 to N are the dependent constants. Means R plus 1 depends upon maybe on A1 or A2 or up to AR, or AR plus 2 depends upon A1, A2 dash dash up to AR. They are what called dependent constants, right? Once I calculate these independent constants, then I can have relations for other R plus 1 to N constants in terms of these dependent constants, right? Independent constants, sorry, right? Then that is how now I'll do dou pi by dou P1, dou P1 leads to dou pi by dou A1 is equal to 0. That gives, right, out of these equations now QP1. However, before I differentiate, what now I'll do is already the degrees of freedoms are specified like this, right? As say QP1 is specified as A1, right? A1. Therefore, there's already known value, students. I hope you're understanding. A1, Q1 is equal to A1, and like that Q2 is equal to A2, dash dash up to the values which are already specified, right? They are now substituted here. Numeric values are substituted, right? And so I'm now differentiating with those, right? Dou pi by dou P1 along the specified boundary condition. I'm differentiating with respect to the degree of freedom with specified boundary condition. First, specified degree of freedom condition, right? Degree of freedom. Therefore, it leads dou pi by dou A1 is equal to 0, or that gives this K K22 multiplied by Q2, right? Plus K23 multiplied by Q3 dash dash up to K2n multiplied by Qn from this second one. Here in the above equation, what I did is just I have substituted Q1 is equal to A1. That's it, right? Q1 is equal to A1, right? Then that is how the equation is equal to F2 on the right hand side, this F2, because this with respect to that minus K21P, this, because I'm differentiating with this Q dou pi by dou QP1. QP1 is nothing but Q1, which is now A1 now, which is A1, right? And so this term which was there on the left hand side will go to the right hand side, making the equation as F2 minus K21 A1. By this time, A1 is already known value, maybe so many mm multiplied by the stiffness, maybe Newton per mm. gives so many newtons, which is directed from that F2. Hence, on the right hand side, I have to have a known numeric value of that force. Net effective force is known, which is equal to this K22, Q2, K23, Q3 dash Q2n, Qn. It is a summation. Like that, if I do the differentiation with respect to the other specified boundary conditions, dou Q divided by dou P2 dash dash up to dou phi divided by dou PR, rth boundary condition, which is specified, dou phi divided by dou r is equal to 0. Now I'll get kn 2 q2 plus kn3 q3 dash dash knn qn is equal to fn minus kn1 a1 kn1 a1, right? Now I'll put the same these equations in matrix format, student, like this, as say k22 operated upon q2, right? K23 operated upon Q3 and K2n operated upon Qn. That is how the first row is equal to F2 minus K21 multiplied by A1. Like that, last row Kn2 upon Q2, Kn3 operated upon Q3, Knn operated upon Qn is equal to Fn minus Qn Fn minus Kn1 multiplied by A1. There is a typographical error here. It must be Kn1. This must be Kn1 multiplied by a1, right? Then once I get this, I'll say this as my uh, modified stiffness matrix. Actually, my original stiffness matrix, structural stiffness matrix, was K, which was n by n matrix. Now this is n minus 1 by n minus 1 size has reduced by 1 because now a1 is eliminated from that, right? And so it is n by 1 by n by 1 matrix, which is called modified stiffness matrix operated upon QM. Even its size also not n by 1, students, it is n minus 1 multiplied by 1, right? Like that, this FM also reduced by one size, right? F2 minus K21 dash dash up to Fn minus Kn1 multiplied by A1 is also n by 1 multiplied by 1 size. Like that, now this is the QM is equal to FM is a modified equilibrium equation just by differentiating with respect to one specified degree of freedom or boundary condition. Like that, you go on doing for the second degree of freedom, third degree of freedom, right? So on and so forth. Then if I do for dou pi divided by dou q p minus r, then I'll get this as modified stiffness matrix. Its size is equal to n minus r multiplied by n minus r. That degree of freedom, displacement degree of freedom is n minus r multiplied by 1 modified, right, value, and modified global load vector is n minus r multiplied by 1. That is how I'll get kq is equal to f. Kq is equal to 1, the equilibrium equations, right? Now I'll get n minus r simultaneous equation. Solving this will get appropriate feasible solution. Right? Now once I get the appropriate feasible solution, means q1 q2 dash dash, which are independent, then later on we'll substitute in the dependent equations, solving which I'll get all the unknown degrees of freedoms q2 onwards. If at all q2 is not specified, if at all q2 is specified, then q3 onwards, right, dash dash, right, up to last degree of freedom I'll get, right? Then after getting that, I'll also get the reactions like this, that rp1 is equal to qp1 multiplied by q1, this one, right? Qp1 multiplied by this first row plus qp1 2 multiplied by q2 dash dash up to qp1n multiplied by qn, right? This is the force minus the force, if any, acting at that point prior to achieving equilibrium, external forces if at all, right, minus fp1, the external forces that are already acting prior to the equilibrium, minus that. This is what that effective force or effective force will go in the form of reaction along that degree of freedom, along that first degree of freedom, or along that second degree of freedom, like that along other degree of freedom. That is how we'll get the reaction, students. I hope you understood the theory. Now let us see an application of this uh, potential energy approach using elimination approach for treatment of boundary conditions, right? Now, uh, this is a numeric problem. A thin steel plate of uniform thickness T is equal to 1 inch and Young's modulus E, or modulus of elasticity E is equal to 13 × 10⁶ psi pound per square inch, and the weight density rho or gamma or F is equal to 0.2836 pound per square inch is as shown in the figure. In addition to the self weight, the plate is also subjected to a point load of 100 pounds at its midpoint. Then what is asked is model a plate with two finite elements, and second one, write element stiffness matrix and element body force vector. And third one is assemble structural stiffness matrix capital K and global load vector capital F. And fourth one, using elimination approach, find the global load vector or degrees of freedom vector. The fifth one is evaluate element stresses sigma, and sixth one is determine the reaction forces at the supports, means RIs, means R1, R2 dash dash dash, right? That is how the thin thin steel plate. Actually, this is exactly the steel plate, student. Right? If I see the density 0.2836 pound per square inch is nothing but exactly 7850 kiloton per meter cube, or 78.5, sorry, 7850 kg per meter cube, or it is equal to 78.5 kiloton per meter cube. Kiloton per meter cube means that is the steel having Poisson's ratio is equal to um, uh, 0.25, right? And the the plate is having varying cross section, student, right? You please see here at the end the right, it is hanging from the support like this. At one end the width of the support is equal to 6 inch, whereas at the after some distance its thickness is reducing to 3 inch. After a distance of 24 inch, its thickness is reducing to 3 inch, from a 6 inch to 3 inch. That is how, this is what called the bar of varying cross section. It is a bar of not uniform cross section, students. It is a bar of varying cross section, right? Within a length of 24 inch, its width or cross section is reducing from 6 inch to 3 inch, right? Then, then uh, what is also given is at the middle length means at 12 inch, an external force, concentrated load, downward force P is equal to 100 pounds is also acting. That is also given in the problem. Then that is how the width is varying from 6 inch to 3 inch. Hence, at mid length of 12 inch, what is that width? I'll interpolate. Therefore, upon interpolation, I'll get 6 plus 3 divided by 2 means 4.5 inch. At that width of 4.5 inch, the load, concentrated load, is acting in the downward direction at the end of that, which is at a length of 12 inch starting from the horizon. Then, and we also know that 1 pound is equal to 0.4536 kg and 1 inch is equal to 2.534 centimeters. Now, I'll calculate uh, what are the widths of these elements, right? Now, I want to do the discretization, student. The very first step in finite element formulations is the discretization, right? Now, in the discretization process, we need to, first step, you create nodes right. Now the rules are like this, that wherever there is a starting of the geometry and ending of the geometry, it requires one node. Means at the starting you require one node, at the end of the length of this member, axial member or bar member, you require another node, three, right? And also the other rule is that wherever the area is changing, there a node must be there at the intersection of such elements, right? Here also you please see that here the area is also changing at the same time. At the intersection of such areas of the changes, there is a point load. Even the third rule is that wherever there is an external point load or concentrated load, there must be a node. Therefore, now this has satisfied two criteria. One, area is also changing as well as the concentrated load is also there. Hence, at the mid length, I'll have another node. Let it be node number 2. The first one is node number 1. I'll move in the positive x direction. This is assumed as positive x direction, student. Then this is the node number 2. I'll move forward. Node number 3. That is how good node numbering is assumed. Good scheme of node numbering is assumed in this node numbering pattern, right? Over 24-inch length, right? Then once I say node numbering is given, the second step is element numbering. Now this is the first element which is shown in circle. First element is connected between the first and second node. Second element is connected to local. First is global 2. Local 2. Second node is global 3 node number. Global 3 node number. Now you please see that if I want to uh, model these two elements, then what are the cross-sectional areas of these two elements? Before that, I'll now calculate what are the widths of these, each of the element. Then average width of the first element. You please see here that the width of the first element was varying from 6 inch to 4.5 inch here. 4.5 inch here, student, right? That is how you please see here. This width was 6 inch, and here the width is 4.5. Therefore, what is the average width of this trapezoidally varying cross section, varying from 6 inch to 4.5? And so now I'll get the average width. Average width is equal to 6 plus 4.5 divided by 2, 5.25. You please see that, right? Whatever this element is directed here, the same part of that element is added here. Means that trapezium, which was having an area of A, is assumed in FEM modeling as a rectangular shape of width 5.25 by a length of 12 inch. 12 inch. That is of the first element modeling, student, right? Similarly, now I'll go to the second element modeling, right? Here, the width of the second element is varying from 4.5 mm to 3 mm. Sorry, 4.5 inch to 3 inch. Hence, the average width of the second element is 4.5 plus 3 divided by 2, which is 3.75. 3.75 means that is how this trapezium is assumed as a rectangular element here. A rectangular element here, right? You can see that at the intersection of this node 2, the width is changing from 5.25 inch to 0.75 inch, requiring a node compulsion there, making a node compulsion there from 1. That the area of the cross section is changing from that point onwards. 2. Also, there is a concentrated load, a point load is also there, right? Because of that, also you require another a node. Therefore, in total, I require 3 nodes. Therefore, this is a 3 degree of freedom system. Hence, this is how the degrees of freedoms at these nodes are noted as Q1 at node 1, Q2, Q3 at 2 and 3 nodes respectively, and also the globe, the loads that are acting along the first degree of freedom are shown as F1 and F2, F3 along second and third degrees of freedoms also respectively. And the length of that first element is now shown as 12. L1 is equal to 12 inch and L2 is equal to 12 inch, student, right? That is how we have discretized this continuum having tapering shape, having varying cross section into a uniform cross section of the first element, uniform cross section of the second element. A1, its area is equal to A1, which is equal to the width 5.25 multiplied by the thickness perpendicular to the plane of the board. The thickness perpendicular to the plane of the board. Student, this one, right? This is how the first element, which is 5.25 by 12 inch, 5.25 by 12 inch. Its thickness is equal to 1 inch. Its thickness is equal to 1 inch. Whereas the second element is this one, whose width is equal to 3.75 multiplied by its thickness. It's a thickness which is equal to 3.75 inches square. Right here, the units are in terms of pound and inches. I'll always be using the consistent units, right? Therefore, here onwards, we'll say all the loads are in pounds and the displacements are in inches. In inches, right? All units must be consistent till the solution is obtained. Till the solution is obtained. Hence, I got areas of the first and second elements, and there's a 3-degree of freedom system which I already discussed, which is 3 by 1 Q1, Q2, Q3 transpose, and also the global load vector F1, F2, F3 transpose 3 by 1 vector. Next one is element connectivity table. Is element 1. We already discussed that it is connected between the global degree of freedom 1 and 2 with the local node numbers or local degrees of freedoms 1 and 2 respectively. And the second element is connected with the second and third global degrees of freedoms as local degrees of freedoms 1 and 2 respectively. Hence, the element connectivity table will establish a relation between the local and global correspondence students, right? Local and global correspondence are local and global degrees of freedoms. Now, next subheading is now the modeling is over. The second bit is over, students. We have modeled an FEM model, right, using two elements only, right? And we have calculated areas, lengths, and here what is given is Young's modulus of these two elements is same because the steel is the material. Sometimes in other problems we'll see that that first element is that of the steel, the second element is that of the aluminum, the third one is that of the branch, like that, right? Therefore, they are what called heterogeneous materials. This is what homogeneous material, student. Right? Young's modulus is same. E1 is equal to E2 is equal to E, homogeneous problem. Then now next subheading is element stiffness matrices. Element stiffness matrix is given by Ke is equal to Ae divided by L 1 minus 1 1 minus 1 1. Then I'll take that of the first element K1. K1 is A1 E1 divided by L1 1 minus 1 minus 1 1. Substituting numeric values, the area of the first element is equal to 5.25 inches square multiplied by uh, uh, 13 to the power 6 pound per square inch. This is inch square inch pound per inch square divided by L. L is in terms of inch, 12 inch, right? All are consistent units. Please make a note. Multiplied by 1 minus 1 minus 1 1. Now I'll get outside the common as 13.125 to the power 6 1 minus 1 minus 1 1. And similarly, doing the same for the second element, I'll get say K2 is equal to A2E divided by L2 1 minus 1 minus 1 1. Substituting the numeric values of length and area of the second element as 3.75 and length 12 inch. Now I'll get the result as 9.375 1 minus 1 minus 1 1 into the power 6. That is why I got two stiffnesses matrices, element stiffness matrices. Now, next subheading, the evaluation of element body force vectors FE, then which is given by FAL divided by 2 1 minus 1. Then substituting for the first element, I'll get F density of the material is 0.2836 pound per inch cube. But the area of the first element is equal to 5.25 inches square, and length of the first element is equal to 12 inch divided by 2. Means the load is distributed half to the first node, half to the second node. Then that is how these are acting along the global degrees of freedoms 1 and 2 respectively. Then its result is equal to 8.9334 pound at the first node, first degree of freedom. Also at the second degree of freedom, same 8.9334 pound. Then doing the same for the second element also, I'll get the result by substituting the values. I'll get 6.381 into 10 6.381 pound along the second. This is the result along the second degree of freedom, 6.381 pound. Along the third degree of freedom, same 6.381 pound. Then one moment. Once we evaluate uh, the element body force vectors also, then what now? is that we will check, is there any traction forces acting given in the problem? Is there any UDL, intensity of the load, so many Newton per mm like that? But nothing is given. Nothing is given. And so uh, there are no contributions to the traction force, surface traction forces. No contributions are there. Leave that force, right? And the third type of force is there any concentrated load along the first degree of freedom? No. Second degree of freedom? No. Third degree of freedom? Sorry, along the second degree of freedom? Yes, there is there. P2 or F2 is equal to 100 pounds. Along the third degree of freedom? No, zero. That is how all the forces are noted down, students. Then the next step is assembly of the global stiffness matrix. Now, structural stiffness matrix are global stiffness matrix, capital K, which is of the size n by n, where n is the degrees of freedoms by degrees of freedoms, n by n. 3 degrees of freedoms are there. Therefore, you open a K matrix as 3 rows and 3 columns, means 9. 9 coefficients are needed there, right? Which is notated by summation of all stiffness matrices, where E is equal to 1 to 3 now. 1 to 3. Right? Then, doing that, now you open row 1, you write here 1, like this, 2 and 3, and also the columns as 1, 2, 3. That is how you open 3 by 3, 9 cells, either in Excel sheet or just in a regular white sheet paper. Right now, what we'll do is I'll go to the individual element stiffness matrices. Now I'm going to the first element stiffness matrix. Now you can see that this is along the 1, 2, 1, 2. As per this element connectivity table, this is along the first degree of freedom, second degree of freedom, first degree of freedom, second degree of freedom. Hence, I'll copy this 13.125 along 1, 2, 1, 2. Right, like that, I'll copy this coefficient 9.375 along second, third degrees of freedom along that, in that IP address, in that IP address, right? I'm doing the same here. I just copied along the first, second, and second in the first row, in the first and second columns, 5.25 minus 5.25 minus 5.25 and 5.25 as that of the contributions from the element stiffness matrix 1. Then there are the second node being common for the first and second element. It is a getting contribution also from first element as well as second element. Therefore, the contribution from the second element in terms of the stiffnesses is 3.75. Here, minus 3.75, minus 3.75, 3.75. Whereas these are the 0, 0. And so that gives a result as 13 to the power 6 divided by 12. When taken as common, it is equal to 5.25 minus 5.25 minus 5.25, 9 minus 3.75 minus 3.75, 3.75, 0, 0. Along first, second, third, and first, second, third rows and columns respectively. Done. That is how the units of this is pound per inch. Here, I think units are not written, student. It must be written pounds per inch. All units are consistent. Next subheading. Assembly of global load vector, notated by capital F, which is 3 by 1 vector, which is having contributions from all the three. One, the element body force vector, right? Right. Now I'll go to element body force vector. That of the first element, we have seen that along the first and second degree of freedom, they were contributing 8.9334 pounds, 8.9334 pounds. And also go to the element body force vector that of the second element, it was contributing 6.381 along second and third degrees of freedom. Now you can see that it is the node 2 is common for the element 1 and 2, hence it is having superpositions from both contributions, right, using law of superposition. That is how the element body force vectors are contributing so many units of the loads in terms of pounds. Now, we have already seen that there are no traction forces given in this problem. However, the same may be there in the other problem, students. If at all they are there, these shall be written as the respective values as we have seen in the case of FE, right? And here for this problem, the element body, the concentrated loads at the first degree of freedom is 0, and the second degree of freedom is 100, and the third degree of freedom is 0. All these are in terms of pounds. That is how element, global load vector is written as a summation of the contributions from the element body force vector, element traction force vector, element, and concentrated loads at respective degrees of freedoms. The summation now works out, say, 8.9334 pounds, 115.3144 pounds, 6.381 pounds, which is 3 by 1 vector, 3 by 1 vector. Then next heading is the displacements. You get the displacements, right? Then once I say I want to get the displacement, then I'll write the equilibrium equations. KQ is equal to F. That is how the K equation, structural stiffness matrix, which is 3 by 3 matrix operated upon global displacement vector Q1, Q2, Q3, which is equal to the global load vector. But students, we already know, actually this gives three simultaneous equations, solving which will get Q1, Q2, Q3. But before I solve, let us examine what are the boundary conditions, right? What is already given in the problem is that first element is connected to the rigid boundary there. Therefore, here QP1 at this point, QP1 is equal to displace in the downward direction. It cannot displace in the downward direction. Right? Then that is how QP1 is equal to A1, in this case is equal to 0, or that is equal to QA1. Means in the elimination approach, uh, I need not calculate what is Q1 from this equilibrium equation. I need to just calculate only what is Q2, Q3, right? Therefore, in the elimination approach, this QP1 is equal to A1 is equal to 0 is obtained by eliminating rho from equilibrium equation, as well as eliminating that column from structural stiffness matrix. Right? Hence, eliminating that first row, the entire equilibrium equation, student, because this P1 along the first degree of freedom, the displacement is already known. It is specified. It is specified as 0. Specified means we know that it cannot displace. Means it is specified as a specified boundary condition is equal to 0. Therefore, that row is deleted. Even in the column, the first column is deleted because that is already specified. Hence, the modified stiffness matrix, which is a 2 by 2 matrix, right? Now this is gone. Only these are the terms that are left, which is now modified stiffness matrix Km operated upon Qm. Modified displacement vector is equal to modified load vector. It gives two simultaneous equations. Solving these two simultaneous equations, now I'll get, right? This is how I'm getting 2.5 10 power 6 multiplied by 9 Q2 minus 3.75 Q3 is equal to 115.3144. And next equation, 2.5 10 power 6 multiplied by minus 3.75 Q2 plus 3.75 Q3 is equal to 6.381. Solving these two simultaneous equations, students, like this, right? Now I'll get that the displacement Q2 is equal to 9.27 10 to the power minus 6 inch. Very small value, 9.27 10 to the power minus 6 inch, right? Back substituting that in either of the two equations, I'll get the degree of freedom Q2. Substituting that Q2, now I'll get Q3 as, say, 9.94 10 to the power minus 6 inch. I think here the units are missing, students. We need to write the units also, inch, all consistent units. And so the final displacement vector, global displacement vector, or simply displacement vector, is 3 by 1 vector along the first degree of freedom 0, second degree of freedom 9.27 10 to the power minus 6 inch, third degree of freedom 9.94 10 to the power minus 6 inch. That is how the displacements are obtained. Then next, we need to evaluate, or we need to find the stresses. We already know this relationship between the stress and strain. That stress is nothing but Young's modulus multiplied by strain, but strain is nothing but that epsilon is nothing but V multiplied by Q. Therefore, we already know for a 1D 2 node element, what is B? B is nothing but 1 by L multiplied by minus 1, 1, which is a constant matrix. It is constant. It doesn't depend upon the position xi or x. Hence, it is a constant matrix. Doing that same, now I'll get for the first element, sigma 1 is equal to E, B, B1 multiplied by Q1, right? E is E 13 to the power 6, and B uh, strain displacement matrix, where B is called element strain displacement matrix 1 by L minus 1 1. Length of that first element is equal to 12 inch minus 1 1, and the Q, this Q is along Q1 and Q2, because you go to element connectivity table 1, that says that these degrees of freedoms are along Q1 and Q2. The first degree of freedom, local degree of freedom, is along global degree of freedom 1. The second local degree of freedom is equal to global degree of freedom 2. Therefore, Q1 and Q2. But by this time, I already know what is Q2. Q2 is 9.27 10 to the power minus 6. Substituting with, now I'll get the stress in the first element. By matrix multiplication, this minus 1 multiplied by 0, 1 multiplied by 9.27 students, it is giving a result. Sigma 1 is equal to plus 23.175 pound per square inch. This plus indicates it is under tension. It is under tension like this, right? Whereas negative value indicates compression, right? The result of this tension is extension, right? In terms of displacements, right? Similarly, you will do the same for the second element also. Say E multiplied by B 1 by 12. B is nothing but 1 by LE minus 1 1, and Q2, small Q2, is nothing but is related from element connectivity table as Q2 Q3, between these global degrees of freedom. But we already know that what is Q2, 9.27 10 to the power minus 6, and Q3 is equal to 9.94 10 to the power minus 6. Multiplying that with outside this constant, I'll get the stress in the second element as plus 1.7 pound per square inch, right? Once I get this, even I'll see that this is also positive, student. That indicates that this is also the tension, right? This is also under tension, pound per square inch. Both are under tension. Now, next, obviously the result is correct because there is no restraining effect at the node 3. Had there been any restraining effect, the element 2 would not have gone under compression. But element 2 is also free. Therefore, element 1 as well as element 2 both are under tension. Like this, right? Because there is no restraining effect at the node 3, like this, right? Now, then in which case it will go under compression. But now the node 3 being free, there is under also extension. Element 2 is also under extension, or the element 2 is experiencing tension only. Now, next subheading, reactions. Now the reactions are obtained along which the degrees of freedoms are specified. Now we'll say that along the first degree of freedom, where QP1 is equal to 0 is specified, there I get a reaction of R1 is equal to that first row, which was deleted using elimination approach. I'm just recalling that first row of that entire equation on the LHS, right? Minus FP1. Already, what is there? What is the force that is already acting at that degree of freedom? If I deduct that, the difference will go in the form of reaction along that first degree of freedom. Hence, substituting which, now I'll get a Q1, Q2, Q3 substituted here, and already in the global degree of global load vector along the first degree of freedom, we already seen that 8.9334 force is already there, right? 8.9334 force is already there. Therefore, I'm just going back then so that I'll show result. Right? This is how that this F 8.9334 along the first degree of freedom already acting. Therefore, the remaining difference will go in the form of reaction into the support, right? Into the support, student, right? That is how the reaction. Then that now works out upon substitution of the numerics as, say, this 5.25 multiplied with 0 minus 5.25 multiplied with this 9.27 to the power minus 6, 0 multiplied with this minus multiplied with this constant minus 8.9334 gives a result of minus 130.6 pounds. Here minus indicates that it is acting in the opposite direction to that of the positive x direction. Positive x direction is assumed in the downward direction. I'm getting minus means this reaction is into the support, right? That indicates that equilibrium. For the equilibrium, it will be into the support, right? Now, let me check the statics check. Sigma V is must be equal to 0, but self weight plus loads due to traction forces plus loads due to concentrated loads or the entire structure or the entire continuum are now calculated. Now, what is the first contribution is self-weight. Self-weight is the width is varying from 3" to 6" from one end to the other end. Average width of the trapezoidal is equal to 4.5 multiplied by thickness. Now I got area multiplied by total length of that continuum. 1D problem 24". Now I got the volume that multiplied by density 0.2836. Now I'll get so many pounds of self-weight dead load. Now dead load is over. Now that now works out to 30.62 students pounds, plus there are no UDL forces acting so many pound per inch, right? So many pound per inch over this prescribed thickness, over that thickness, right, in the form of UDL. That is not there, hence its contribution is equal to 0 plus point loads. Yes, point loaded. Node 2 is only acting. There are no point loads at node 1 nor at node 3. If at all they are there, you please add. Either add if they are acting in the positive x direction, you subtract if they are acting in the in the opposite direction. In the opposite direction, they are acting in the positive x direction, hence plus 100 plus 100. All the if they clubbed added, it works out 130.62 is the total downward load that is acting. But what I got from the previous calculations is also the same, minus 130.6. Therefore, this downward force is equal to this upward force. Hence, the statics check sigma v is equal to 0. That plus this is equal to that minus this is equal to 0. That is how the elimination approach. I hope students you understood the treatment of boundary conditions. One specified boundary conditions using elimination approach. Using this elimination approach. Nothing will conclude this session. Thank you, students. Thank you for your watching this video. If you like this video, please do click like, share, and subscribe to our YouTube channel. We will meet with another topic in the next video. Till then, bye bye.